Hello everybody, thank you for joining us. Today we will be discussing software-defined data centers and two of the leading software-defined data center solutions, Cisco's ACI and VMware's NSX. My name is Justin Jett, I'm the Technical Marketing Manager at Plixer, and I'll be moderating today's webinar. Today's presenter is Bob Noel, Plixer's Director of Marketing and Strategic Partnerships. Now, before I begin, let me first make a note that ACI is a trademark of Cisco Systems and NSX is a trademark of VMware, a subsidiary of Dell Technologies, and that the comparisons outlined in this presentation are not a full representation or endorsement of either product and are based on observations by employees of Plixer. So with that, I'll hand it to Bob.
Thank you, Justin. During today's webinar, we will discuss the definition of a software-defined data center, as well as the terms underlay and overlay. We will review the two market-leading options for a software-defined data center, Cisco ACI and VMware NSX. I'll then discuss the impact a software-defined data center has on traffic visibility and troubleshooting. According to Wikipedia, in a software-defined data center, all elements of the infrastructure, networking, storage, CPU, and security are virtualized and delivered as a service. Now, as far as definitions of underlays and overlays, I would like to share my own opinion on this. I define an underlay as the physical network infrastructure, or the switches and the routers. Traffic forwarding decisions are handled on a next hop basis with traditional layer 2 and layer 3 protocols. Now for the overlay, I define that as a software that sits over the physical network and abstracts forwarding and filtering decisions based on the needs of applications and devices. When we get a little further into this presentation, we'll actually discuss a couple of practical applications for each. When it comes to helping people wrap their brains around the concept of a software-defined data center and why the industry needs to move there, I personally like to use an analogy of a GPS for applications. For this analogy, consider yourself getting into a car to go somewhere. In the past, to get from point A to point B, I would have gone to MapQuest, typed in my starting and ending points, gotten a turn-by-turn set of directions and printed them out. I would have brought the directions with me and placed them on the passenger seat so I could reference them as I drove. Now, let's say I get on the highway and for some reason traffic is all backed up. Now in this case, I have no choice but to sit in traffic and wait. I only know the next hop directions that I got from MapQuest. Today, instead of printed directions, I would actually use a GPS on my phone like Waze. In this case, I enter my destination, get in the car, and go. Now, when traffic on the highway is congested, Waze can have me take an exit and find a better path. The application has awareness of the entire road system, or the analogy in this case, the network capacity, and it has context for how the road system is being used. If all the cars on the highway used Waze, the app would distribute traffic across the roadways, getting everyone where they needed to go and better utilizing the capacity of the road system. Now consider the idea that a software-defined data center is basically like a GPS for applications. There is context of the applications, application mobility, resource elasticity requirements, and a full understanding of the network paths and available capacity are available in that GPS. Okay, let's take a look at the two leading software-defined data center solutions, starting with Cisco ACI. Cisco's ACI delivers a programmable fabric solution. With ACI, Cisco takes an integrated overlay approach. This means the solution is a combination of both hardware and software. Cisco ACI is based on the Nexus 9000 family of switches. The Application Policy Infrastructure Controller, or as I'll call it here moving forward, the APIC, is the key architectural component to the solution. It is the unified point of automation and management for the ACI fabric, policy programming, and health monitoring. It is a centralized, clustered controller that optimizes performance, supports any application anywhere, and coordinates unified operations of both physical and multi-tenant virtual environments. As a side comment, while APIC acts as the centralized policy and network management engine for that fabric, it is not in the data path, meaning the fabric still forwards traffic even if communication with APIC is lost. I mentioned that here because it's a common question that I hear. Multiple virtual switches are supported for the hypervisors within Cisco ACI. Cisco, in fact, has their own application virtual switch, or AVS, and they support VMware's distributed vSwitch as well. Cisco has a robust partner ecosystem. Open north and southbound RESTful APIs are the basis for this open ecosystem, and the APIs enable orchestration across management, infrastructure, security, and application service domains. All right, let's take a high-level look at how these components are put together as an actual implementation. Now, first, the data center network is built on a leaf spine architecture. Again, that is based on Nexus 9000 series switches. Every leaf switch is connected to every spine, but leaf switches are not connected to each other, nor are spine switches connected to each other. Within ACI, this leaf spine connectivity creates the IP fabric, which is treated as a single entity when it comes to configuration and management. Cisco APIC is deployed as a highly available 3-server cluster redundantly connected into the fabric. For additional redundancy, servers are often dual connected to leaf switches and can either be virtualized or bare metal. For virtualized servers, APIC pushes configuration information to the vSwitch on the hypervisor. Within the APIC GUI, you have the ability to define endpoint groups and associate virtual machines or bare metal servers to those endpoint groups based on their common policy enforcement requirements. In this case, I've defined endpoint groups based on how a 3-tier application traditionally gets deployed. So there are web, application, and database endpoint groups. Now, these 3 endpoint groups are then associated with what's called an application network profile, or ANP. This ANP contains the policy contract defining how the web, application, and database tiers of this single application can interact with each other. So to review, within the Cisco APIC GUI, you A, define your endpoint groups and the policies associated with each, and then B, assign them to application network profiles, which include the contract for how the endpoint groups can actually interact with each other. A final point to make on this slide is that for a 3-tier business application, virtual machines can also be isolated within an endpoint group using microsegmentation. APIC updates the infrastructure with all this knowledge, and now applications can be easily deployed. And when VM or application mobility occurs, server to server, rack to rack, or row to row, the ACI fabric is aware of the move and automatically enforces the policy at both the physical switch and the virtual switch interfaces across the fabric. Here, you can see a screenshot from the APIC GUI itself. And that's showing that not only is APIC aware of the fabric interconnections, the network interconnections, but it also has awareness of each virtual machine, the security policies associated, as well as the provisioning requirements for each application. That's how ACI acts as the GPS essentially for this fabric. Let's now review value propositions of ACI. First, let's look at operational efficiency gains. ACI offers unified management for both physical and virtual networks. It can be used to automate network provisioning and troubleshooting, supports service chaining, and takes a centralized approach to fabric programmability, which we've talked about. That allows it to provision any VLAN, any subnet, anywhere. Application requirements are automatically understood by the fabric to ensure those capacity requirements are met. That is what a programmable fabric is all about in this case. And again, I go back to the analogy that I used in terms of a GPS. That's how it handles the dynamic and programmable fabric. ACI's centralized management enables consistent provisioning and security policy enforcement as applications dynamically move throughout the data center. Policies are defined per endpoint group and endpoint groups are associated with application network profiles. This ensures the application receives the resources it needs, even if it moves physical location. In addition, the hypervisor agnostic approach ensures that applications can exist on any server. Centralized service automation is supported for firewalls and load balancers, etc., so those things still can interact with the fabric. There is support for both virtual and bare metal endpoints within the endpoint groups, and as I mentioned, you can use any hypervisor in your virtualized environment. Open RESTful APIs enable departments like server and network teams to better collaborate. They also offer resource orchestration, technology integration, and overall freedom of choice. And that ecosystem we talked about earlier is, again, another example of where that fits. Application health scores, endpoint awareness, and a single view into applications, latency metrics, and drop counts across both the physical and virtual machines provide visibility and help with troubleshooting. That includes multi-site and or multi-tenant deployments. All right, next, let's review value propositions as they relate to security for ACI. If the security and network teams want to use that, or this feature, right, service automation for layer 4 through layer 7 network services provides automated security provisioning and service stitching. Security policies can be enforced per tenant, per application, or per workload. Microsegmentation provides stateful awareness of east-west VM to VM traffic. The fabric delivers secure multi-tenant isolation and segmentation by application, or as needed for any group-based security policy down to the microsegment or the VM itself. ACI policies are dynamically pushed to the switches across the fabric, eliminating the need for manual and complex configurations. And within the fabric, you have application level visibility into the traffic. All right, that covers Cisco's ACI at a high level. Let's now transition to the components of VMware's NSX software overlay. As mentioned, there will be an existing network infrastructure comprised of any manufacturer's hardware and any architecture. It could be leaf and spine, or it could be the traditional 3-tier hierarchical approach. It just needs to have IP connectivity across the data center. Now let's look at the logical network overlay. Here we have the data plane of NSX. Essentially, the network edge has been moved into the hypervisor with virtual switching, routing, and firewall capabilities. The control plane consists of the NSX controller, which is also deployed as a cluster of 3, like APIC was. It sits over the physical network with an awareness of all of the logical networks, as well as knowledge of the physical network paths. Forwarding topologies are defined within the controller, and the separation of the control and data planes means that forwarding decisions are made in both the hypervisor and the infrastructure, and I'll cover that in a little bit more detail on my next slide. NSX Manager is a centralized configuration portal for the software-defined data center, and APIs here allow the exchange of data in and out so that you can interact with other management applications as well. Really, that means that NSX Manager can be the main GUI, or users can leverage vRealize or OpenStack or some other cloud portal to act as that primary management interface. Okay, so here I'll attempt to provide an example of how NSX encapsulates and forwards traffic, and then I'll summarize what I covered. As I said, NSX abstracts the physical network and sits on top as a software overlay. In this case, we have a leaf spine data center that could be comprised of any vendor's switches. For this example, we'll attach 2 physical servers, which are on the purple 192.168 network. The server on the left is in .1 purple subnet, and the one on the right is on the .2 purple subnet. In this network, the spine switches act as a layer 3 boundary across each of the server racks, and this is an example of how many physical networks are built and subnetted. Each of the physical servers have virtual machines on them. For this example, we'll put the virtual machines on the blue network and place them both on the 10.1.1 subnet. VXLAN encapsulation is used to enable layer 2 adjacencies even across layer 3 boundaries. This is what allows virtual machines on the same subnet to communicate with each other regardless of where they physically reside. Within the hypervisor, there is a distributed virtual switch, or vSwitch, and we've talked about these prior. On the vSwitch, there is something called a virtual tunnel endpoint, or VTEP. Now, the VTEP's purpose is to maintain tables that map virtual machine addresses to the addresses of the physical server on which they reside. In doing so, they become the key to VXLAN encapsulation and being able to get the traffic across the network. In this network, when the Blue 1 VM wants to talk to the Blue 2 VM, encapsulation is required. Now, since these two VMs are in the same subnet, but they physically reside across a layer 3 boundary, right, because they reside across that spine layer, without encapsulation, a traditional network would not be able to deliver that traffic. So, to fix this problem, the VTEP encapsulates the header, looks in its table to find the IP address of the purple physical server, and adds a new header to the front of the packet. The packet is then sent across the physical network. When the packet reaches server 2, the purple header is stripped off and the packet is delivered to Blue 2. The Blue 2 VMs are not even aware that they are separated by a layer 3 boundary or that their traffic is being encapsulated. As far as they know, they are in the same layer 2 domain with each other. Now, if you didn't follow all the details of this example, that's okay. The main takeaway here is that by abstracting the physical network, NSX allows you to place virtual machines anywhere in a single data center or across multiple data centers at any time. Traffic can be tunneled through the physical network for successful inter-VM communication, and this can occur without the need for manual network configuration. Okay, NSX provides strong security value propositions. Firewall policies can be embedded into the hypervisor. Microsegmentation is accomplished through stateful awareness of east-west traffic. Virtual machine traffic can dynamically have policies applied. The VM isolation can be used to support multi-tenancy on a shared infrastructure. You can logically create a demilitarized zone, or DMZ, per application anywhere in the environment. And you can secure end-user access to any VM. NSX also delivers strong automation capabilities. You'll hear VMware talk about IT automating IT with infrastructure on demand, and personally I would summarize this as delivering automation value across the traditional IT silos, network, server, and application teams. APIs enable cloud-like agility or orchestration and capacity elasticity or resource elasticity. NSX enables VM mobility to occur across traditional layer 3 boundaries, layer 3 network boundaries. NSX delivers application continuity value as well. Network and security policies are mapped to specific workloads. Disaster recovery is easy with the ability to support active data center deployments. And application migration across private and public cloud boundaries is made easy as well. Okay, now when you're evaluating your options for a software-defined data center, personally, I advocate you ask several questions that can help you gauge which solution may be the best for your environment. First, what is the gap between what you currently own and what you need? And you want to ask that both from the perspective of hardware and software. How do I migrate from my current state or from your current state, right? What are the steps that get you from point A to point B? How long will it take to implement from the starting point to when you actually want and need the value from the solution? What's the operational impact? So often there can be quite a bit of work in upfront and in the short term before those savings are seen, and you want to understand what that process actually looks like. What customers that look like you have made the transition? Ask for references. This is a rapidly accelerating space. Both NSX and ACI are gaining a lot of traction in the market, and it's very likely that they'll be able to provide you with examples of customers that are much like you. And finally, we want to ask, how will the solutions be able to integrate into your existing monitoring, troubleshooting, and security tools? So as a side note, just to comment on sort of which ones, I think a lot of people ask me which one's the right solution for them. I've seen a lot of examples of customers that are choosing ACI, they're choosing NSX, or in fact, in a lot of cases, what they're actually choosing is they're choosing to deploy both at the same time. When both are deployed, customers really get the advantages of the programmable fabric that Cisco provides within ACI. It in fact treats NSX as an optimized application. And then when you overlay the NSX solution on top of ACI, NSX's tight integration with VMware-based data center designs gives you a lot of flexibility and, again, integration at the virtualization and hypervisor level. All right. Now, the last question that I asked there prior to that, the one about how it integrates with existing troubleshooting and monitoring tools, that's a very important question to consider for the purposes of end-to-end visibility. Regardless of which solution you choose, ACI or NSX, moving into a software-defined data center dramatically changes the forwarding paradigm of what is the most critical traffic on your network, meaning the traffic in your data center. Both ACI and NSX alone offer traffic and application visibility within their own solution. So there's pretty good visibility within the fabric, within that existing domain. But they also both export data to third-party visibility and reporting systems like Scrutinizer from Plixer. ACI exports NetFlow version 9 as well as some additional metadata, and NSX exports IPFix. Now this is really important because the full extent of traffic flows extend from the user across the Wi-Fi network into the wired edge and distribution closets before they get to the software-defined data center and cloud. You need to be able to associate all of the flow data together as it traverses the entire network to gain true end-to-end visibility. Scrutinizer from Plixer can consume telemetry from across the entire network, including ACI and NSX software-defined data centers, all the way out into the public cloud, stitching it all together for rich data context and true end-to-end visibility and reporting. NSX exports IPFix data. So here we have a screenshot of Scrutinizer ingesting the data and giving you the ability to visualize the overlay traffic inside that VXLAN encapsulation. You can see the tenant source and destination, which represents the flows between the VMs themselves. Now, traditional third-party tools that are not able to consume and understand these IPFix exports will only see this as encapsulated traffic traversing the physical network. It would be sort of similar to what happens with a GRE tunnel or SSL encryption. You'd see the source and destination of the traffic based on the physical network addresses, but you'd lack the ability to see the tenant traffic or the encapsulated traffic. And you would lack the ability to correlate that traffic with the flows that extend across the network user, across the network all the way out to that user. On the next slide, you actually see an example of a screenshot from Scrutinizer showing NetFlow version 9 data, which is what Cisco ACI exports. Now, because ACI does not encapsulate the traffic, the fabric switches see the original source and destination of all traffic. As I mentioned earlier, there is tremendous value gained by exporting this information to Scrutinizer. The east-west data center flow information can be correlated with the data that Scrutinizer receives from all corners of the network. That can be from the wired and wireless network. It can be from Cisco's ASA with Firepower or Palo Alto Networks firewalls. It could be from Gigamon or Ixia appliances, as well as many other points of telemetry. Again, the important point is here to gather points of telemetry from all across the network, not just one, and be able to stitch that together for true context and end-to-end visibility. All right, so let's recap what we've covered during today's webinar. Let's look at Cisco's ACI. ACI is an application-aware programmable fabric that includes both hardware and software. It supports physical and virtual servers. The security policies are dynamically enforced through the creation of endpoint groups. And remember, endpoint groups are where you can also group VMs, or is where you group VPN, can't speak here. It's where you group virtual machines that require the same security policy. This allows for microsegmentation and multi-tenancy. ACI reduces the complexity of network configuration in a highly dynamic and mobile data center environment, and it exports NetFlow version 9 and metadata to third-party tools. For VMware's NSX, VMware's NSX is a software overlay that abstracts the physical network and uses it as a pool of transport capacity. It brings the network edge into the hypervisor with virtual switches, routers, and firewalls. NSX abstracts the hardware to enable geography-independent VM mobility. Security enforcement is embedded into the hypervisor, supporting microsegmentation and multi-tenancy, again, within the hypervisor itself. And from an export perspective, it exports IPFix. Scrutinizer consumes the flow and metadata exported by both ACI and NSX to correlate, visualize, and report on the virtual and physical environments that make up your network. The entirety of data flows expand from the user across the network, the Wi-Fi network, into the wired edge and closets, all the way into the data center and even then into the cloud. Scrutinizer delivers network traffic analytics to provide visibility, context, and reporting for cloud, network, and security domains. All right, so I hope you all found this webinar helpful and informative. Remember, it was intended to be an overview of why software-defined data centers are necessary, to provide an introductory overview of both ACI and NSX, as well as highlight the fact that forwarding and filtering decisions within the software-defined data center are made in a different fashion. You will visualize and troubleshoot these environments with some different tools than you may have been using within traditional Layer 2 and Layer 3 routing and switching environments. ACI and NSX provide visualization themselves, as I mentioned, but importantly, they export some information to third-party metadata tools like Scrutinizer to give that true end-to-end visibility. All right, with that, I'd like to thank you all for your time. And this was intended to be a fairly high-level webinar and overview of two complete solutions, but I hope this has been helpful to everyone, and thank you again for your time. All right, Justin, now back to you.
Thanks, Bob. It looks like we have time for a few questions. So the first one is, how does white box implementation, or how do white box implementations affect ACI and NSX?
Thanks, Justin. Yeah, that's a great question. Again, I'll mention that I don't represent Cisco or VMware myself, but I'll give you my interpretation of an answer to that question. So NSX will be unaffected essentially by the introduction of white boxes into the data center, and it will be the software overlay abstracting the physical network infrastructure no matter what brand of switches you have, right? It could be white box, it could be anybody's. So NSX would be fairly unaffected by that. ACI is a little bit different. Remember, it's a combination of hardware and software. It's actually quite a lot different. It's a combination of hardware and software that delivers that programmable fabric that we talked about. As we went through from a components perspective, it is based upon the Nexus 9K series of switches. So the fabric itself needs to be built out by those 9K switches. So it's my understanding that those white boxes would not be able to participate in the programmable fabric. But the reason for that is the value add that you get by combining a software and a hardware solution together. The capability of the software interacting specifically with that hardware is how the endpoint groups and the application network profiles are enforced within the fabric.
Okay, so the next question, and this question is about Scrutinizer, is how does Scrutinizer correlate traffic across the physical network with what is happening in the software-defined data center?
Thanks, Justin. That's a good question, and I definitely should revisit that. So there are actually a number of ways that information is gathered and correlated across both your physical and virtual environment. Scrutinizer consumes flows and metadata from any device that exports it. So your switches, your routers, your wireless controllers, your firewalls, and then as we talked about during the webinar, right, as well as the data that's being exported from VMware, ACI, and NSX itself. So all of this information is available as structured data within Scrutinizer's database. So reporting can be done against any of that information. Let's kind of walk you through what it might look like here. So consider the example of a caller reporting a poor experience with a specific application. So, caller picks up the phone, calls the help desk, and now how do I figure out root cause and understand what's happening? Is it an issue in the software-defined data center, or is it an issue across the physical network? So what you do is you go into Scrutinizer, because Scrutinizer has all of the flow information that's available from the network regarding that user. It's really easy to query the database against the username and the specific application with which that user is having trouble. This gives you really good visibility into the health of the network itself. You get things like latency and bandwidth utilization and lots of other metrics that provides you, again, across that physical network. And what you now can do is you can correlate that information with what's happening within the specific microsegment of the software-defined data center that's been defined for that application. So we walked through and we talked about how NSX does microsegmentation. We talked a little bit about how ACI does segmentation or microsegmentation, and the ability to correlate the flow information that's exported from those solutions regarding these specific microsegments is how you gain that end-to-end visibility. Those things can be essentially stitched together. And in fact, for even additional insight, what you can do is you can use flow data timestamps from Scrutinizer to further investigate what you're trying to identify based on data that server logs have created and maybe exported into your SIM like a Splunk, which, by the way, Scrutinizer integrates with as well. So there are lots of different ways that you can correlate the information from the physical environment into that of what's happening in that software-defined data center. The key value of Scrutinizer is that it takes a third-party approach to gathering flow and metadata from all the points of telemetry that we discussed, and it delivers that complete end-to-end view.
Thanks, Bob. We have time for one more question. So the question here is, which solution, ACI or NSX, provides better security?
Thanks, Justin. Yeah, that's a tough one. I'm not sure there's a clear answer to the exact question of one being better than the other. ACI and NSX both take different approaches from the point of enforcement, but are both working towards the same goal of protecting information inside the data center. So, traditionally security tools like maybe a next-gen firewall, they've been deployed at the point of ingress and egress of the data center. And although that model's still good and people can and should still deploy those products at the ingress egress of the data center, it does leave all the east-west VM to VM traffic uninspected in that case, unless you hairpin it into the network, which is not a very good use of capacity. So what ACI and NSX both do is they're both looking to provide microsegmentation in a multi-tenancy security environment within the virtualized and software-defined data center. So NSX places switching, routing, and firewall capabilities into the hypervisor, as we talked about, and it becomes the point of enforcement. ACI uses policy enforcement per endpoint group and application network profile. I guess I'd describe ACI security and enforcement as happening within the fabric, as opposed to NSX is happening more, again, at the hypervisor and in that virtualization environment. These different approaches are another reason why I actually see companies deploying ACI and NSX together. The security approaches that each take complement each other. Hopefully that actually answers the question.
Thanks, Bob. And thank you all for joining us today on our webcast. If we didn't get to your question, feel free to send me an email, justin.jed@plixer.com, and I'll be sure to respond as quickly as I can. Until next time, have a great day.